Okay, we're solving inclines, problem 1. We have a cart sitting at rest on a frictionless incline. It's going to accelerate down the incline. And the free body diagram, no matter how we break up the vectors, is going to look like this. Normal force perpendicular to the ramp, mg down. I'm drawing my incline as very narrow, or shallow, not steep, so that I can tell pretty easily where the angle is in my diagram. So I can either break normal force up into two pieces along the x and y axes. mg I don't need to break up because it's along the axis. So the question is, which of my angles is my theta? Well, my given theta is this tiny little angle here, so it must be this tiny little angle here. It's the easiest way to figure it out. This one is adjacent, so it's the cosine component, and that one is the sine theta component. So f net in the x dimension, I'll use right and up, is n sine theta. F net in the y dimension is n cosine theta minus mg. But look at the direction of the acceleration. I have my acceleration is this way, so I have some acceleration in the y and some acceleration in the x. So both of these are unbalanced. ma x and ma y. So that's kind of a pain there, that I have the acceleration is in two pieces. If I break it up this way, though, such that my axes are parallel and perpendicular to the ramp, n I don't need to break up at all. mg, though, I need to break up into a component going down the ramp and a component going into the ramp. So I've again made a right triangle with mg as the hypotenuse. That's always how you break up a vector. It's a right triangle with the whole vector as the hypotenuse. And again, it's easy to tell which angle I want because it's the skinny one. Because that's how I've drawn it. If you draw it like it's 45 degrees, then you have to do a bunch of geometry. So this one is opposite the angles, mg sine theta. This one adjacent, mg cosine theta. I'll pick down the ramp and out of the ramp. So parallel to the ramp, all I have is mg sine theta. And perpendicular to the ramp, I have n going out and mg cosine theta coming in. If I look at my acceleration, none of that is perpendicular to the ramp. It's all parallel to the ramp. So it's balanced perpendicular, and the whole acceleration is in the parallel dimension. So this one on the right here is much easier to solve because there's a 0 here and the a is all in one piece. So I can really easily solve that by canceling the m's. And it's g sine theta, which is 3.42 meters per second squared. So an interesting interpretation here is sine theta is always less than 1, which means that the acceleration of a cart on a ramp is always less than g. And if it were equal to g, that would mean sine is 90 and it's just falling down.